Hello and welcome. Here we are, part 4. Oh man, I feel like there's like so many things I should do or could do or whatever. I'm just like overwhelmed with need to work. It's gotta work. Anyway, all right, whatever. I'm not gonna complain. Try not to complain too much. I don't know. I don't even know what I'm complaining about. Okay, so I want to return to this problem. Kind of feels like smacking my head into a wall at this point because it might not work, this so-called optimization that I'm really at like drawing straws here as far as like what to do to make this faster. Hopefully it works. Maybe it works. It might not work. Who knows? I'm gonna be annoyed one way or the other. I'm already annoyed. Just want to get it over with, I guess. I don't even know what to do after this. I don't know, man. I don't know. I'm just gonna keep going. See if we can get there. And then, I don't know, take another break and go take a nap or something. Who knows? Who knows? Frustrated, tired, cold, whatever. Not kind of hungry. I'm not hungry anymore. I guess at some point I have to eat. I don't know. Whatever, man. I'm just complaining. I don't know. It's alright. I'm not gonna keep going. Let's just try. What to say about this? So, yeah. A minute and a half complaining before I start. All right, read the problem again. 2282 expression add operators. Given a string num that contains only digits and an integer target, turn all possibilities to insert the binary operators, addition, subtraction, and/or multiplication between the digits of num so that the resultant expression evaluates to the target value. Note that operands in the returned expressions should not contain leading zeros. Example 1, 2, 3 looks like this: 1 times 2 times 3, 1 plus 2 plus 3, target 6. Both of these evaluate to 6. 2, 3, 2, and 8. 2 times 3 is 6 plus 2 is 8. 2 plus 3 times 2 is 8. Both of these evaluate to 8, and so on. 0, 0, you can't have 0, 0 anywhere. You have 0 times 0, 0 plus 0, 0 minus 0. But 0, 0 itself, there's no leading zeros, that doesn't work. And then here you have no way of getting 91, 91 from this sequence. So we're going to, we came up with a solution, and actually we can get rid of this. This doesn't really speed things up very much. There's a pre-processing step that I did here, but it's actually better to use, this, I think. This works too. Change this from a recursive algorithm to a dynamic programming algorithm. And we have a algorithm, but the problem is this is too slow in most cases. So what we're going to do is we're going to add a limiting condition, another limiting condition, to try to prune parts of the add a limiting condition to prune parts of the algorithm such that, so this basically, what this does when we're searching a search space exhaustively for solutions that'll work. What we want to do is prune parts of that search space such that it's not so expensive in terms of time to search that search space. Now, I'm really irritated at this point by this question, among other things, because one, that intuition that we need to prune and what we could prune is one of those things that, like, it's not necessarily an obvious thing, but knowing that that's necessary is very not obvious. I guess you'd have to run through a few tests to realize that you time out. But particularly, the algorithm itself is an exhaustive search, which means that if you just make the input sequence like 1 or 2 more characters, then it doesn't matter how much pruning you do. It's gonna be a really long time for the algorithm to complete. So I guess I'm trying to say is this is a really inefficient algorithm. I don't see, maybe there is a faster way to do this that I'm just not realizing. I don't know, I kind of almost hope not, because I'll be really sad about it. Like, oh, there's a really fast way to do this, you just couldn't do it, you just didn't do it. There's a chance the pruning doesn't even help, which I think it probably will make a big difference, the pruning. But you could sort of conceive of situations where pruning wouldn't help too much. But yeah, so like, if it is the case that this is just like a pruned exhaustive search, and that it won't be fast enough unless you prune, like, that would just be extremely irritating. If there is a much faster way to do this that I just don't realize, like, yeah, it's probably the case, not probably, but there's like a chance of that. I don't see it though. This seems like way too complicated for there to be like a more efficient way to do this. I don't know, maybe I'm just not seeing it, but anyway, okay, I'm gonna try. So yeah, I'm just complaining a lot. There's a lot of other pressures in my life too that are really difficult at the moment, and this is like running into this wall of a question is frustrating. I've been really cognizant of my hair lately, just because I'm noticing. I think I'm losing my hair. I think my hair is receding on the hairline. It was always kind of high up there, but more recently I'm really starting to notice it for whatever reason. So that's that too. Keep looking at it, noticing it. It's like also this particular angle, kind of like, for some reason I'm just noticing how much there isn't hair here and there is hair here. Let's talk about my hair instead of solving problems. That's where my mind is at today. Anyway, I'm just extremely irritated. Just irritated for a number of reasons. Alright, so let's try to focus here. So what we want to do in order to prune this algorithm, what we want to do is pre-process the numbers that we're building. So at each step you'll notice we're building numbers. We want to pre-process these numbers such that at a certain iteration we can say, okay, the rest of the numbers we have to work with, we know what they are, and so depending on whatever number we have at that point, we can say, hey, we don't need to process the rest of those numbers, because it won't be possible either through addition, subtraction, or multiplication to ever reach the target that we're trying to get to. So like, you can actually stop here, I think halfway through this one, for instance, and you won't need to go all the way, because you know the rest of these, it won't be, there's no combination of numbers here that you can use that'll give you addition, subtraction, or multiplication will take 3, 4, 5, 6, 2, 2, 9, 1, 9, 1. Or really most of the possibilities that you can get up to this point won't be able to go that far. So yeah, so there really aren't. Yeah, so you like kind of cut in half the sort of input size, something like that. That's kind of what we're going for, some kind of pruning like that, which ultimately is not going to speed the algorithm up that much in general, but it will speed it up enough for this particular input size. That's kind of the idea. It's kind of what we're going for. How we're going to do that is we're going to actually, this pre-processing step is almost the same, except it's going to be the numbers, and these are all integers. Now they're not integers. I'm sorry, they're longs. And pre-compute is not the string. number associated with the range of digits, or the range associated with the substring of num. And actually, for this pre-processing step, we don't need to be clever at all. We can actually just say these, we'll just say 0. Those should never really be touched, but we'll just initialize them anyway. And this is just going to be string to I. String to long should be. So we'll just use a parsing routine. That should be fine. Now we can take array of ij for current and just set current equal to. And we were saying these should be I minus 1 and j minus 1, both of these decremented by 1. So we do this. This should still give us the right answer, hopefully. Not j, I rather. I starts off at A, and we decrement. These might have to be swapped, actually. Wrong. Nice. Okay. That's kind of annoying. It should be A and A minus 1, A minus 1. I starts off at A. Also, this is a little confusing. They're using I instead of, so I and J up here. Actually, A is on the right side, so A's on A's on the other side. I think that's what I was saying before, is that this gets a little confusing. Okay, there we go. So this is not, this pre-processing step doesn't really help us that much, but what does help us is now we can calculate these efficiently, and then we can do a comparison of what's left over. So yes, so we can do skip leading zeros. We can also say skip impossible branches. Prune impossible branches. And that's the goal here. That's what we're trying to do. So we say if the current value, so long, we'll just call it t, and we'll say t is going to be the rest from left to right is from left to right, the number that we're looking for to process is going to be to the end, so it's n minus 1, and it's going to be from A to n minus 1, right? Yes, wherever A is to n minus 1, that's the rest of what we have to process. I'll call that T. Now it's not current, it's going to be the value of the previous possibilities. It's actually going to be inside here. Of the previous possibilities, yeah, we actually need to do the pruning inside a little bit more. So what's interesting is we might have some number. Yeah, that's kind of part of the problem here too. Is this is like got a little bit complicated. If I got an interview question like this, I'd probably just stop. I'd probably just give up. It's like, no, man, this is way too complicated for 45 minutes. Yeah, this is like ridiculously complicated, or at least the approach I'm trying to take here. I don't know, maybe in the discussion they have some very clever approach. Anyway, we'll have to take a look at that and see what they have in the discussion. But anyway, so what you would need to do is, can we prune a multiplication? Well, you know what? It's even easier than that. You could just say, yeah, actually, easier than that. Don't need to go that hard. Don't need to think that hard about this. Actually, it's even easier. I think it'll still be effective enough for what we're doing. You have t, so alpha and beta. We'll call it alpha is actually going to be from 0 to a minus 1, so even larger than, and beta is going to be a to the end. Yeah, you could do even better than that. You could do even better. Just say, take the largest possible number that you have at this point. Oh, no, I can't. Oh, so annoying. Hate this question. I'm sorry, you're wrong. I'm wrong about that. We do have to go all the way. Dude, this question sucks. Oh. Or this approach sucks. I don't know. That's painful. It's frustrating. No. I was gonna say all you have to do is just take the largest number you can make. But it's not about the largest number you can make. It's your current number. You actually need to know what you currently have. Part of the problem here is that if you're dealing with this approach that way I'm trying to do it, you don't actually know what the multiplicative values are going to be. In other words, you're like sort of halfway processed throughout the algorithm because you're trying to process multiplication before processing addition and subtraction, so you kind of have a running total for your multiplications. So what does that mean? It means you can't prune in a really simple way. It means the pruning gets really complicated, because if you have some multiplicand that you're considering, so I think I need to rewrite how we're approaching this such that we can actually evaluate. We can make an evaluation and say, okay, this is what the left side is done, and then whether or not we can continue on the right side based off what's on the left side, then we can decide to prune or not. The problem is that we're constantly in a halfway. I'm so annoyed. I'm so annoyed by this problem. This is like, that's fine normally if you're just gonna brute force, because why would you need to prune if you're gonna brute force? Because it's brute force anyway. I'm really irritated. Extremely irritated. All right. So what do we do? So we can we could prune. I mean, we could try it. So we can't prune. All right. So at the moment, we could possibly write a new algorithm, and that could be possibly pruned. So like, I still have to think about how that would be. First off, I have to think what even would be that algorithm, because I have an idea, but I don't know if it actually works. That's one. And two, I don't know. Don't even know how I'm going to approach that. And then I don't know. I also don't know. Excuse me. Maybe I could prune that one, and then I don't know how could I even prune this one? Is it even possible? So there's that. So there's like three things to think about here. One would be the other algorithm. Two would be how can I prune it, and three is how can I prune this one. Excuse me. So pruning this one, as I mentioned, I could try to force the evaluation of the operation that's currently being like kind of rolled forward. Part of the problem with that, though, is could actually make the number totally different than what other possibilities would be. Yeah, that doesn't make sense. Because if you force that, then you force all the multiplications to happen, you force the additions and subtractions to happen. And that's not necessarily the right spot to be in compared to where the target value is. So I think we just can't easily or reasonably, I wouldn't say easily, I'll say just reasonably. I don't think we could reasonably prune this as written. Like that's the conclusion I came to before. It's just too difficult with this kind of rolling forward concept in there, enmeshed in the exhaustive search. Can you? Yeah, I'm gonna say it's probably not feasible. Like there might be a way to do it, but I don't know. I don't know what it is. I don't know. It's not obvious at all. Yeah, it's really annoying. It's extremely irritating. Okay. Excuse me. Okay. So. So. Okay, so what else? What is next? I don't think it's possible to. I don't think that it's possible to prune this algorithm as written. I don't think so. I think it'll be too complicated. Now, actually, you could prune the addition and subtraction portions, but the multiplication portion, that, I don't know. I don't know what you would do there. The addition, well, maybe that's all we need is the addition and subtraction parts. I mean, maybe that's enough. Actually, maybe that's it. Yeah, that's all we need. I'm hoping that's all we need. If we have to do the multiplication part, I'm gonna be annoyed. Or if it's not enough, I'd be annoyed. Well, I'll be annoyed anyway. I'm already annoyed. I'm already annoyed no matter what. Regardless. Okay. So T is going to be array of A to N minus 1. And we're going to say, so we want to add So we've calculated the previous, that's the process amount. So if the process amount plus t is not large enough, less than 9191, or the target, less than the target, then oh yeah, okay. I was gonna say we're not using lambda expressions anymore, so I don't need to scope things. Basically, if we can't add the maximum possible to this, and we're still going to be less than the target, then we can prune this part of the branch. Yeah, man, I don't know. Suddenly very cognizant and irritated by my hairline. I don't know why it suddenly got me. Yeah, I guess I don't know. Anyway, okay. All right, so we want to. I'm not gonna worry about it too much. I'm gonna throw some water in my hair later, I guess. If we can't possibly add enough to the value and we're still gonna be less than the target, then we're not going to add here. So only in situations where we are where we exceed this target, where we're going to add these two together and be greater than or equal to the target. On the other side, if we subtract this amount, we need to be able to reach the target. I don't think I articulated that correctly before either. Yeah, I guess we don't need that. I could leave that. Okay. So if we subtract, so now what's interesting is we're going to, processing the right side really. Yeah. So if we subtract t and we're still greater than target, this needs to be less than or equal to the target. Yeah. So that's confusing. So we need to be able to, if we subtract this and we can't get down to the target, that's an impossible branch. If we add this and we're not above the target, then that's also impossible. Something like that. See if that works. See if we still get the correct answer. Runtime error. Okay. Wow. Okay. Oh, I see. It's supposed to be a-1. And well, actually, it's supposed to be a+1. So I guess t is just 0. Let's just throw that in there. A is less than n, and otherwise we'll just take 0. Something like that. Wrong. Shoot. No, I can't do it that way. No. You know what we can do? You can put a less than n over here, I think, as well. So you don't even perform this check. If a is greater than or equal to n, or these two, something like that. So yeah, you kind of just skip It's still really slow. So it doesn't even matter. It's still really slow. The speed boost we get from doing this doesn't even matter. That's upsetting and frustrating. I'm so irritated. I don't know what to say. Just really annoyed. Just really annoyed. What do I do? What do I do? If I get rid of this, I'll still get the right answer, but it won't even matter, because it'll be really slow. Oh, I guess it does speed up a bit. Yeah, that's kind of what I said. It's like twice as fast. Yeah, okay. Alright, I guess it is a little bit faster if we do this. But it's wrong now, for one reason or the other. That's kind of all we need. We're trying to get through 26 test cases, so we've I think we'll just barely make it if we can get this right. Well, we're missing some parts here, huh? Alrighty. My output's way too short. Seems to be the issue. Why did they bring that to? Whoa. So there are way more that are expected. We didn't prune the multiplicative branches, but we did prune. Yeah, well the deal is when you update the addition or subtraction, you're going to update the process value here. Yeah, and then we can check. If a is greater than or equal to n, and we skip checking against t. Why? So these don't prune properly, is what you're trying to tell me? Come on, man, really? Yeah, well, it may be possible. I think it's got to be both. I think it's got to be both the difference between t and, yeah, I think it's got to be this way. I think it's both of these are the absolute value of the difference between the two. If that exceeds the target, I think that's when it's got to be less than or equal to the target. Yeah, I think that's the idea. And you do both of them at the same time. You either lose both of them or don't do both of them. Maybe that's what we got to do. Let's try that. I don't know, some way to prune this. There's got to be some way, something. Wrong. I don't know, man. Why is it why this doesn't work? So yeah, I mean, if you're looking at 34562 and 37490, there's no way to get to the target, because if you add all of this to this, well, I guess the argument is that you could subtract part of it or add part of it, but if you subtract it, then you could do that, potentially subtract. Yeah, because you get down to 3,000 or so. You get down to a negative number. So subtraction would actually work in this case, but addition wouldn't work. Well, See, that's confusing. Yeah, so I guess I don't know. I think there's no way to prune this. Maybe I'm wrong about it. There's no way to prune this doing that. It doesn't even matter. No, it's just I get to look at my receding hairline a little more and be frustrated again. I'll be right back. I'm gonna throw some water in my hair just because I'm feeling upset, frustrated, insecure, a myriad of other negative words. I don't know. I don't know what to do here. Like I'm out of ideas. Out of ideas. Yeah. Oops. I guess. Yeah, because there's no real pruning you could do because there's just so many different possible combinations here. There's no way to say that you could stop right there. I mean, yeah, because you could subtract 30,000 or 37,000 or something from this and get a number that's less than 10,000, and so you can keep going. I don't know. Now I happen to know that multiplying this all the way through is not going to be enough to take it down. Like, I guess you could say probably this wouldn't be enough. I think what we'd have to do is actually go to the other approach that I was describing before, the recursive approach, where you would do like where you can actually kind of like close the loop on what the recursive results would be over a certain range from I to J, and then from there you can say like, okay, this is what we have so far. Does this give us does some combination of these things give us the result we're looking for? So specifically, you could do a multiplicative term on the left side, add or subtract something on the right side, and then recurse on the right side. And then the sequence of multiplicative terms, obviously there's lots of different, that might even be a recursive routine itself, what all the different multiplicative ways to multiply those digits together might be. Yeah, I don't know, we could use like quote unquote double recursion, something like that. Do that on the left side, memoize, no, it's not memoized. Yeah, I guess you could memoize that actually, I'm thinking about it, yeah. Quadratic number of different multiplicative terms you can make on the left side. Excuse me, actually it's more than that, I don't know what it is. It's like, I want to say it's cubic. It's actually a lot of different ways you can make multiplicative terms on the left side. And then on the right side, for each of those terms, you would either add or subtract and recurse on what's left on the right side. And then each possibility left to right is like another chunk you can have of possible multiplicative terms. Yeah, I think that's a better way to do this. And the reason why is like, I don't know, the pruning that we can do is pretty much the result of the recursion on the right side can be placed into a hash set, a map, where the key is the target value, and then attached to that key is the number of as a vector of strings or a queue of strings, however you'd want to do it, or yeah, vector of strings of possibilities that can give you that target amount, that specific amount. And so you could take if we're adding, we could take the difference. If we're subtracting, we could take the sum and see if that key is in the set that we just generated by recursion. And that's a way more efficient way of looking for the possible solutions than what we're doing here. So I think it's another brute force approach. It's just more efficient. I think that's all we can do here. I think it's pretty much it. I think pruning is just not. I think we got to kind of like make that quote unquote pruning like part of the algorithm itself. Yeah, I'm gonna go ahead and I don't know, man. Just go stare at my hair. Yeah, I'm just kind of noticing that. Like you can kind of see that there's way more hair up here, and not as much hair over here. And I'm just I don't know, kind of irritated. Kind of just overall irritated. Too many. I don't know, so many problems. Maybe just making a big fuss over it myself. Maybe it's just me. I like the just shave everything off haircut. I've been doing that from time to time because I kind of know that I'm gonna. Something tells me I'm gonna end up losing my hair one way or the other. I don't know if I'm wrong about that, but yeah, I'll be right back. I don't know. I think we just gotta take a different approach to this algorithm. I think that's it. It's just it really is still just a brute force, but slightly better somehow. I mean, even a cubic number of multiplicands is okay. It's just how to generate all the multiplicands. Yeah, I guess I don't know. I guess it's like a subproblem. Like that's not too hard. It's not. I think I'm making this out to be more difficult than it is. You just think, how would that work if you had like how many ways you can generate? How many different? Yeah, like generating the list of multiplicands that you can have by placing these multipliers as described. You could. I guess that you could do kind of a multiple recursion there where you can say, okay, I'm going to take this digit here and this digit or this number here and this number there, multiply the two of them and put a multiplicand in the middle. But you could also do that recursively where you say, find all the multiplicands that you could have on the left side, all the multiplicands you have on the right side, all of their associated sequences and numbers, and then take the Cartesian product of each of those so you could pair up across that multiplicand that we select in the middle between the two of them. That's kind of a lot, actually. If that sounds like it's a Catalan number, which is a very large number, actually, of possible multiplicands. Yeah, that could be kind of rough. Catalan number is a big number. Actually, before we go, okay, I think I'm making a big fuss over my hair that I shouldn't be making, but can we even do this with the calculator? Oops. I think we can, right? Catalan number looks like what? It's basically 2n choose n. And it's exactly when you are taking Cartesian products. Or it's related to Cartesian products, like summations over Cartesian products. 1 over n plus 1, 2n choose n. Yeah. It's quite the number. Not 42 non-crossing partitions of a 5-element set. Yeah. Below the other 10 of the 52 partitions. So that's what Catalan numbers are related to. Alternative expression looks like this. And Um, Dyke words. I remember reading this before, years ago. This is, yeah, you see this? Segner's recurrence relation. That's your summations over Cartesian products is Segner's recurrence relation. That's what I was getting at. Because that's if we split, right? We take two subcases and we split over some index, and we say that we're going to put a multiplication symbol somewhere in there, and then on the left side we're going to repeat the same thing. The right side repeat the same recursively. The number of times you can set up Catalan, number of ways you can produce multiplications on the left side, the number of ways you produce multiplications on the right side, and then we're going to combine all of these, right? We're going to take all of these sets together, but each set is going to be first a decision of a multiplication left to right, and then all of the possible combinations, which is the Cartesian product, which is multiplicative, would be, for when you were to count all of these, you'd multiply, and then we're going to add all those together. That actually is the Segner's recurrence relation, I'm fairly certain. So, great. I think I'm going to throw some water in my hair anyway, throw some water in my face, just, I don't know, some cold water. I feel like I'm way too, what's the word? Agitated today. Too agitated. Yeah, so that's Segner. I'm fairly certain Segner's recurrence relation is what we end up with if we try to produce just the set of multiplicative terms that we could have by placing multiplication symbols. Dude, this question is so much harder than is obvious than you might realize. This question is crazy. So this is 1 over, and so this is just for the number of multiplications that you could do. And we said we might have 10 for a number, so this is 20 choose 10 over 11, which is 20 factorial over 10 factorial over 10 factorial over 11, which gives you 20, 19, 18, 17, 16, 15. Well, actually, we could just throw that in a calculator. I didn't really want to calculate that. I just wanted to know, yeah. I don't know if this has combinatorics on it, this calculator. We can do 20 factorial divided by 10 factorial squared divided by 11. Okay, that's actually manageable. Only get 17,000, under 17,000 different multiplicands that we could have. Okay, we can work with that. That's fine. Sizable, but that's okay. All right. So then, sure. You know what we ought to do? We ought to generate have a vector of integers for each range pre-computed, do that recursively, And then when we perform our recursion with addition, subtraction, and multiplication, we can just refer back to that array that we've already computed, pre-computed array of 17,000 elements. I think that's a good idea. I think we can do that. That's fine. That works out okay. Should we? And I think actually we should put that into a set of a map, also into a map of numbers, and we have the numbers or the values, and then the strings that produce those values as multiplicative strings that we can combine those pieces with addition and subtraction, and we can say, yeah, we could easily use those maps, the keys in those maps to do what I was describing before, where if we don't have that possibility, right, the difference between, if we're adding or subtracting, the difference between what we currently have and the target, if we can't do it, then we don't have that solution. We won't have that solution. All right, okay, all right, fine. I won't go throw water in my hair. I don't know. I'm just suddenly self-conscious about my hair. I don't know. Okay, so we can do, I think we can do this. Pre-processing step to determine multiplicative terms. Possible in a specific range of values. From I to j. All right, something like this. So yeah, we'll have an associated set of strings for a given. I'm going to use an unordered map, but that should be fine. We're going to say multi or mult map or something, mult memo, or just a possible mult. Yeah, something like this. And we're going to say for int I equals 0, I is less than n plus plus I, j is going to be I, j is less than n plus plus j, and we're going to say, so we're going to do this using dynamic programming, which is kind of peculiar. The way it's going to work is we say for some integer x equals I to x less than or equal to j, or really should be less than j. So this is just going to loop over all of the possible ranges for I and j. And what we're going to do with x is we're going to take a point between I and j, and we're going to say that I to x is the left side and x to j is the right side. And we are, so I to x inclusive is the left side, and x plus 1 to j is also inclusive. Yes, so x could be equal to j. As long as x plus 1, I think it's got to be x plus 1 has got to be, because if you go, now you can create the entire, you could take the entire number, and maybe actually we should, perform this first pre-processing step. So I did this wrong. Okay. 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 Oh, wait. Okay. Didn't need to copy the first one. All right. So we do want we do actually want that first pre-processing step where we decide on so we can get the particular number given I and j, right? And then now we want the possible multiplications over that particular range, which is kind of a subproblem that we're going to solve here. And what we want to do over each range is actually split the range with x and say calculate the left side of the range and the right side of the range. Now what's interesting is the x plus 1 has got to be less than or equal to j, because it's going to be inclusive between x plus 1 to j and x to I to x. So I to x inclusive and then x plus 1 to j inclusive. The problem with that is that you might have I to j is the one part at the end. We're going to actually add that too. So we're going to say possible mult of array of I, j, and it's going to be a queue of strings, I think I went with. It really could be kind of whatever you want. I think it might be easier to use it might be better to just use a vector strings. I'm not sure quite yet what should be here. It's some kind of a container of strings. Might be better to use a vector initially just because I'm not sure exactly what we're going to put in there. I think it will construct and then whatever associated string. This string at this juncture is actually just it's actually just a direct conversion of which is kind of awkward. Okay, toString, we could also take the substring. Both cases, we're going to get this string back. Maybe we should do, I mean, you could do both, right? Why not? But I think it's going to make a copy anyway. Could do this as well. That actually might not be a bad idea. So now you don't have to do this operation later on as well. Okay. So my thinking here is basically when x is j, you're not going to process this. You're going to just take the whole left to right portion as just one multiplicative possibility. Yeah. Yes. So that's when I and j are equal to each other. Also, you'll get this iteration. So you don't. So this is when you break, if you can break into pieces. Now, what you're going to do when you break into pieces is you're going to say, you can actually do something like this. Reference v is this. Should construct the vector, I believe. And so you can push back v here, and now you can say, oh, no, I'm wrong. I take that back. No, I'm wrong. No, that's wrong. Okay, so now what you can do is say, with our multiplication, we have possible mult. I kind of want to name it something other than possible mult, like just array, or I don't know, v or x or t or some I don't know, some name. So call it possible mult. Is going to be from I to, now it's an integer. We no, we want over a range. Yeah, this is not exactly what we're going for. This is also really confusing. No. Oh, this is awkward. I think it's actually an array of, so it goes like this. It's an array of tuples. Of this is awkward. So what do you get? Your multi-dimensional array over this range, what are you going to get? You're going to get a whole set of strings and their associated integers. And actually this is what you're going to return is a map. Oh boy. Wow, what a data structure we have going on here. Whoa. So yeah, okay. Because in that range you can get the same number multiple times with multiple different strings. And what you're going to do, right, okay, I see. So you have two different ranges to consider. So the range of numbers, what it returns is actually, given that range, it's going to be indices into a multi-dimensional vector. Excuse me, and that multi-dimensional vector is going to return, when you try to get the result there, that is going to give you a map of integers to, yeah, okay, that's interesting. Okay, yeah, this is quite the data structure we got going on here, quite the combination of things here. I think this works. So now we can say from I to X is the left side. We'll call that left side. And then the right side is mult of X to J, X plus 1 to J. So the left side with the right side, and what we want to do is we want to loop over the left, take the Cartesian product of the left and right sides, which is going to be, for each of these integers, you're going to loop over the other integers, add them together and combine the strings and create the see, that this part's confusing too now, or is confusing now. There's going to be a resulting ij, so we're going to have a resulting map of integers to a vector of strings. Yeah, this is quite the program we're writing here, and it's this result that we push back. and it's going to be actually result of array of I, J. Yeah, look at that. That's what we're pushing back into. Our result vector here. Yeah, yeah. Okay, I get it now. So we have left and right. We're going to loop over both of those. For on the left side and the right side, we have for each key const. Well, you could use a pair. Well, you could do. Yeah, I mean, const. It's something like this: P1 in left side and P2 in the right side. I'm going to create this val, which is going to be P1 first plus P2 first. That's going to be the key, the new key, and then const string s or new s. That's going to be a concatenation with a multiplication sign between them, right? So you've got the left side and the right side. So it's P2 second and P1 second. Yeah, something like this. And then each of these are going to be added to the result vector, which is it's going to be a result of val pushback new s. Yeah, so you can see both of these could be sort of inlined. All right, that hopefully makes some sense. It's quite involved. That is quite involved. And what I'm wondering is, does this work? Can we do it this way? So, yeah, I mean, it should work recursively. I don't know if this does work. We can, possible multi, we could do. We can just go ahead and comment this out. And return, just return some empty set. And check first if this compiles. We could start with that. Okay. Sometimes, by the way, the hash function evaluates slower than the logarithmic comparison function in map. I think that's why. Oh. I was wondering what's going on there. Are we doing on time? Okay, an hour in. Invalid binary expression. So I think it's because of these. Won't allow me to do that. No. Invalid operands to binary expression. Is it this? Is that the issue? None of these are const. It's a little confusing. Let's think here. So Left, right, these aren't constant. This is a const, that's fine. Why can't I do this? What's the problem? Isn't this a string? What? Need to escape that maybe? Oh, no. I don't think so. That wasn't the problem we had before. Invalid operands to binary expression. Basic string. Can we not? What? Is this concatenation not a thing? And what is going on? Hello? That's weird. What is going on there? What? Oh, because this is a vector. I'm sorry, that's why. Oh, that makes sense. P1, P2. Oh, that's so confusing. Oh, look at that. Oh, wow. Oh, that's really confusing. But that worked. That makes sense. You actually need to loop through. Oh, that's really confusing. Huh. That's super confusing. So the problem is that the number could have multiple ways of getting. Oh, wow. So you're looping over all the possible numbers and then combining them with other numbers. Oh, I see. Oh, that's very interesting. Okay, that's peculiar. You could end up with, this actually should be a set rather than a vector, because you actually want this to be unique. You can have it on ordered set too, that's fine. Don't really need a map. This should actually be an unordered set, believe it or not. Oh, dude, there's way too much going on here. This is way too complicated. You actually need to go through both of these. Yeah. String 1, string 2. This is going to be P1 second. And you're going to say result value dot pushback insert. It's not going to be pushback. Insert S1 plus S2. Whoa, that is quite the doozy. Wow, no kidding. Okay. Huh. Does that compile? I don't know, man, but wow, that's quite the. Okay, compiles. Now, if we loop over all of these, could print some of these, I guess. afraid to do this, but there should be like thousands of them. Oh, okay. Yeah, all right. There's nothing, just none of them. Don't have anything in any of them. All right. Well, that's interesting. Huh. Oh, that's because we need to actually set possible mult ij equal to the result. And set that map at that point. Is that what we need to do? I don't know. I don't know. What is even going on here? This is so confusing. All right. Sure. This is really quite the program we're writing here. I, J, and then we can say we'll just say size, I guess, or just X. I don't know. Just call it alpha. I don't know what we want to name it anymore. We want the result. So it's not, so, yeah, we want just like the size of result. And we're just going to call that alpha. I don't know what to name it. Runtime errors, undefined behavior. Nice. Okay. Oh, that's probably prop plus J. Okay. Okay. So I0, J is 0, we get alpha 1, and then I0, J is 1. I0, J is 0. We don't enter this loop here. I0, J is 0. And we don't enter this loop at all, right? We just go right here. Insert into the result map. Insert this string. Okay, that's fine. And we set the result map for that range 0, 0 to that result map. Okay, print that. Next thing we do is J is 1, create another map for 0 to 1, and we say X is I, which is 0, X plus 1 is 1, which is less than or equal to J. So we can perform this operation. Now, the problem is that nothing exists on the, so I think we just need to create the initial, I think we just need to create the base case, more or less, the quote unquote base cases. So yeah, from 0 to 1, we're not going to recursively create the case here. unfortunately, we assume that we've already created the case at this point. So that, I think, is part of the problem. We aren't doing this recursively, so it's a little more challenging. Actually, we're going to run into that problem continuously. Can we do this non-recursively? Yeah, if we've already computed these parts. But have we up to this point? No. No, we definitely have not. How can we? Is there a way to compute those recursively? I mean, we could, yeah, as I said, we could do it recursively, but I'm trying to not do it recursively. I'm trying to already have those ready. In that case, you want to do all of the sets of 1 first, consecutive sets of 1, then the consecutive sets of 2, consecutive sets of 3, all the way up to the consecutive sets of, yeah, because the consecutive sets of 3 require 2s and 1s. So actually, I think you need to add another loop in here. So you do each of the consecutive sets. Starting with, yeah, so we just need to add another loop in here, I think. And that's relatively straightforward. So it's just going to be for int k. We're not going to go ij. We're going to go with I and k. And we can just say from 1. So it's going to operate a little bit differently. K is less than or equal to n plus k. And what you're going to end up with is I is a starting point, k is the size, and k is actually going to be, it's going to be k plus I is going to be less than or equal to n, or less than n. Yeah, so if k is 1, it's k plus I minus 1. If k is 1, right, that includes I minus, yeah, well, not I minus 1, but k minus 1 starts off at I. So if k is 1, you'd be at I. If k is 2, you would do I minus, I minus 1, or excuse me, if k is 2, you would, I think this makes sense. So k is the number of characters of each section. So you could think of this as like, when I is n, you'd want this to be n minus 1 index, and then it's actually kind of awkward. It's actually I minus 1 minus k, or excuse me, how does that work? It's I minus 1 minus k. Yeah, that's really awkward, but is that right? It's bounds on k. It's a bound on k. So if no, that doesn't make sense at all. I'm sure that's k plus I plus minus 1. Yeah, it's k minus 1 plus I is actually what it is. That's the right way to think about it. Because if you subtract 1 from k, now you're working with indices, and the I plus kth index should be stopped at right before n. Yeah, it's a little confusing. I think k minus 1 plus I is probably the best way to think about it. Anyway, so what we want to do is say x is equal to I. X plus 1 is less than or equal to, it's not j anymore, but it's k. And it's actually I plus k, which is confusing. So X is a lot like K. So now the range you're operating in is I to I plus K minus 1. Yeah, so end up with X plus 1 is less than or equal to I plus K minus 1. We should just do I plus K minus 1. Again, I realize that's a little confusing. We have a left side, right side. Now that's all the same. That's sort of like J. And the difference here, though, is we're not looping over. Oh, this is the difference. I'm sorry. We're putting K on the outside now. That's the difference. Yeah. And I think that's probably we could do the same thing with J as well. But like I said, it's a little easier to understand what's going on here. So we're going to do each of the sized 1 sections, and then we're going to do the sized 2 sections, and then size 3, and so on. And in that way, we'll have the components that we need will already be generated. So this should work a little bit better. K is less than or equal to n. I did this wrong. So K is less than or equal to n. And then now I is less than, I plus K is less than, minus 1 is less than n. That makes more sense now. Yeah, I think that's what we want. Undeclared identifier J. And this is, we said J is effectively I plus K minus 1. We can rewrite that as J. It's effectively J. So here we know what J is. Here we know what J is. Here we know what all these spots we know what J is. It's the second index that's larger than I. Okay. There we go. Yeah, so now, yeah, here we go. Now you can see all these. Oh man, 150,000 more characters. There we go. Those are all the multiplicative terms. Now it's working. Okay. That's much better. Hey, we did it. All right. Or we didn't do it, but we at least got the multiplicative terms right. These are all the sort of Catalan. Oh yeah, we don't print these ones, but we could print those ones too. Sort of the single integer versions. Yeah. So now you can see all these different combinations of multiplicative terms. Something to mention here too is all these different numbers we could produce. There's so many of them. There are so many. As I said, there's like 16,000. So, and then the characters each have like 10. So that's really interesting. But what we might want to do is, what's peculiar about this are the leading zeros. So we actually don't need to worry about leading zeros at all here, because we process them already with, and because we use sets, duplicates are handled nicely. Yeah, because we use a substring and we parsed out the integer. We have both the integer and the string. Oh no, you know what? We don't have yeah, this doesn't work well with leading zeros actually. I'm looking at it. Oh no. Actually, no, we can make the last one, or actually make the first one leading zeros. But it does this relatively quickly. That's the main thing. This is done relatively quickly and saved into our, yeah, there we go. That's kind of a problem. Yeah, that's not good. So we want strip any leading zeros. So this will work nicely, but this won't be correct. How do we get rid of the extra zeros? Remove any leading zeros. So we could say just for so int k equals I, and then say for increment k. And we just say could do something like this. Const int val standard s2l of t, and we can say if we do both of these, we could say val is not equal to 0. Well, actually, even if it is 0, we still want to get rid of the leading zeros. How do we get rid of leading zeros? We can say k could be I, and we just say as long as I is not the last, or as long as k is less than j. Yes. We don't want to go past the end. K is less than j, and we could check here. So we could say s or num of k is equal to 0. Something like this. And that gives the substring. I think that'll handle the leading zeros. Oh. Nope. We still get 0, 0. We don't get 3 zeros. Oh no, wait, nope, nope, nope. What? Huh. Really? Okay. Maybe it's gotta be less than or equal to, I don't know. Invalid argument. We still get all these. Brother, what is going on? What? How do we get these? 0, 0, 0, 0, 0, 0, 9. That shouldn't be. J is to the right. J starts off at I. J is less than n. K, J increments to the right. K is I. If this number K is 0 and K is less than J, which it is always, but sometimes it is, you increment K and you just take your substring for T to be K and J minus I plus 1. I suppose it would be J minus K plus 1 at that point then. I think that maybe that's the issue. Don't take as many characters anymore. Ah, there we go. Okay, that's better. That's what I did wrong. Okay, makes sense. Got it. Got it. So that gets rid of leading zeros, so that's good. Good, very good. How do we process these things now? Well, what's interesting is even though we remove leading zeros, they're actually not supposed to be. I think you're supposed to skip them altogether. Skip values with leading zeros. What do you do? What do you do? You could have a skip array too. I think that's the right way to do it. So if, okay, that's a lot better. That's way better. I like that. I like that more. Let's have a skip array. So if num of I is equal to 0 and j minus I plus 1 is greater than or equal to 1, or greater than 1. Then skip of I j equals true, and we continue. How about that one? Right, as long as you have more than one character, and if you have more than one character, that's j minus I plus 1, and the first character is a 0, that means that you have a leading 0, and you can skip. And that means we have skips in our with empty strings that we've got to process. And we would say skip of ij is false. Otherwise we'd set it to false. And now I'm starting to think I should make this a struct rather than a 3 different arrays. Maybe I should. I can think about that. Let's go ahead and say it depends whether or not we should skip these array of I, array of j. Yeah, we would just skip those all together. So if skip, if not skip of I and j, then we can insert them. Don't know if we have to modify the other pieces of code at all. Oops, what did I just do? Curious what this will do. Hi there. Hello, Migtail Wolf. Welcome back. Hello, hello. This is not my proudest moment here. struggling rather deeply with this question, with this problem. Oh, there we go. I think it works. So now we don't have the leading zeros in there, the multiplicative terms. All right, so I think it might be a good idea to break this into struct. I don't know. I'm tempted to. Yeah, so I was working on this problem for a while now, a few days, and I've been struggling. I've been struggling. See, we're hour and 40 minutes in. Say we're approaching like 8 hours we spent on this now. This is like kind of a really hard problem in my opinion, or has been. So the approach I'm taking, I'll give you the problem. It's given a string num that contains only digits and an integer target, return all possibilities to insert the binary operators addition, subtraction, and/or multiplication between the digits of num so that the resultant expression evaluates to the target value. Note that operands on the returned expression should not contain leading zeros. So 1, 2, 3, target 6, you get 1 times 2 times 3, or 1 plus 2 plus 3. Those values to 6, 2, 3, 2, you can do, and target 8, you can do 2 times 3 plus 2 is 8, 2 plus 3 times 2 is 8, right? 6 plus 2 is 8, 2 plus 6 is 8. Both of those give you 8. 1 of 5 gives you another similar thing, right? 10 minus 5 gives you 5. 0, 0, you can multiply zeros, add zeros, subtract zeros. And then finally at the end, you have this very long string in 91, 91, and there aren't any solutions that give you that. And this can get really complicated, by the way. You can get like, if you have like 1009 and 9, or like these two. Take a look at the expected values for these ones. Right now, my that should be easy. Oh no! Why don't you give it a shot? Why don't you give it a shot? Come back and tell me how easy it is. Not to be too snarky or what the word, I don't know what the right word would be, but not as easy as it looks. Not as easy as it looks. At least that hasn't been for me. So, yeah. So there's a lot of different ways this can happen, right? If you look at the bottom, quite a few different possible permutations of things, or different combinations of things, different possible ways this can happen. So the approach that I took originally was a simple brute force approach using some recursion, and then I said, okay, it's too slow, so let me try a DP solution. So I modified it to a DP version, and that's still too slow. And what it did, I also had to like make a bunch of modifications because it wasn't working. It was too slow, and it also had issues where the what was the problem? Too slow and had issues where it's too slow and had issues where when I was trying to combine addition, subtraction, and multiplication, there were issues with operator precedence. So I had to like come up with some pretty convoluted way of trying to address that, which is what you see here. And it was kind of gross. So the real problem that I had though is that because it was too inefficient, had to come up with something that was faster somehow. But the problem with that is I couldn't really think of anything faster other than maybe pruning, and excuse me, maybe pruning in my search, because I'm basically performing exhaustive search, and I realized I couldn't really prune the approach that I took. It was like way too complicated to try to figure out how to do that. So now I'm going to try a different exhaustive search that hopefully I can prune. So that's the idea. And I'm starting with generating all of the multiplicative possibilities first, start with that, and then so now I have like a map. If I take a range I and j, all the different possible multiplicative terms. So if you, excuse me, if I print this here, then we can see. Now I'm also tempted to switch this over to a struct of things. Excuse me, instead of basically the return value be a struct rather than three different, not return values, but yeah, I guess three different pieces of skipping. There's a skip portion, an array portion, a number portion, and the string. So so what I did, the first pre-processing step is I took the sequence of numbers and I said, okay, something you may have not noticed, by the way, is that you can use any size of number here. So like 1,000 is valid, right? In this previous, if you take a one with a bunch of zeros and a 9, you could split this up with 1,000 over here. So it gets pretty significantly complicated when you can kind of include the numbers as different pieces. But anyway, so pre-processing step in quadratic time to figure out whether or not we should skip that section of numbers, figure out what that number is as a number, and then also what that number is as a string. So we get the string, the number, and whether or not it should be skipped, meaning whether or not it has a leading 0. That's what I did this first pre-processing step, and I was thinking maybe each range should have, maybe just make this a range struct or something, and then set those values that way. And that way, when I access those values, I don't need to have all of these indices all over the place. So that's quadratic time. Then we do another quadratic. This is actually a little more than quadratic time. This is a Catalan number in terms of time. A Catalan number is a combinatorial number. So this figures out how many of those ranges of numbers. For each range of number, it's going to create an unordered map from integers to a vector of strings. And what it's going to be is this map is going to represent all of the different ways that particular range, all the different multiplicative numbers that we can generate. So if we put multiplication signs wherever we want, wherever we could, all the possible results. And the way we're going to store this is that obviously some of these integers could be the same integer, so we're not going to have just a huge list of tuples. We're actually going to use a map, and we're going to map to an integer as the key all of this, an unordered set of strings that can get us that particular key. So that's how we're going to represent all the possible ways we can add multiplication symbols within a specific range. So I and j inclusive, that range of digits we select, we want to figure out all the multiplicative ways we can set up those strings and all the different numbers we can get from all those multiplications. Again, the way to do that is related to the Catalan numbers. It's ultimately a combinatorial expression, and the reason is that basically the recursion goes something like this. Given a particular range, stick a multiplication sign anywhere from splitting into one character and the rest, all the way to 2 characters, 3 characters, etc., all the way to the other side where you have only one character on the right, so a left and right side where the left side has 1 character, 2 characters, 3 characters, the right side has the remaining characters, and then you move all the way, process all of those different possibilities recursively, the left and the right sides, and then until you have, right, the left side is almost all the characters and the right side only has 1 character. So that all of those different possibilities, there's a sequence. Each one of those, the left and right side, you're going to determine those recursively, and then for each of those, once you've done that, now when you combine the left and right sides, the way to actually compute the whole range with that multiplication in that spot is to actually loop over all of the possibilities on the left side, and for each of those possibilities, loop over the parts on the right side and combine them. So you have kind of a Cartesian product of the left and right parts. So that gives you, the reason it's a Catalan number is that it satisfies if you were to count all of these, it satisfies what's called the Segner recursive formula. So that's what that looks like, is basically if you have a range of something, or numbers, if you take the sum over all of the splits multiplied by each other, right? So all the Cartesian products would be multiplying the sizes of those, and you're adding all the splits. So all the like sort of the recursively operating on the left side, and then also multiplying that result by the recursive operation of the right side. That gives you what's called the Segner's recursive formula. So we know there's a Catalan number for all these multiplicative terms, and they're all stored a little bit more efficiently by being stored on the key, on the integer. That, fortunately, in this case, if we have only 10 numbers to work through, producing all of that only takes a few milliseconds because it's only like 17,000 in the worst case things to generate. So we have a matrix of 17,000, at most 17,000. Now it could be a little more than that because we have technically where the number of ranges we're operating on is, but it's I think it's no more than twice 17,000. I want to say. Because all the smaller combinatorial numbers are quite a bit smaller, and basically we're just adding up all of those different combinatorial pieces together. So it's it's more like maybe like less than 50,000, I'd say. In this case, the largest range is going to be 17,000, but like I said, there are a whole bunch of smaller ranges because we're going through all I and J possibilities. So yeah, so those are all Catalan numbers. The largest one being 17,000. So we could do a pre-processing step before we do anything else, which is not too expensive. Now the actual algorithm we want to do, what we want to do is, once using that set of possible multiplicative terms, we want to go left to right, and we want to say, okay, pick a spot again and either add or not add, put an addition or a subtraction there. And we're going to say, we can have on the left side, you can have any of the multiplicative integers, right? And on the right side, you're going to recurse, and on your recursive results, which is going to be very similar to the unordered map that we have already for the multiplicative portion. If any of the left side, if you subtract the left side from the target, so you loop over the pieces on the left side, if you subtract that from the target, if you have something on the right side that satisfies the integer you're looking for, in other words, if it's a key in that map, then that's a possible solution, and you're going to combine all of the strings associated with that key on the right side with all the strings associated with the range on the left side, which really would just be a multiplicative term. And that's for a single addition. Now what's interesting is how we're going to recurse is or a single addition or subtraction, right? And we also have for subtraction, it's somewhat slightly inverted, but it's about the same idea. For the right side though, when you recurse, what's interesting is that you're also going to do the same thing where you have a now that's what I'm kind of struggling is that we don't know. I think what we've got to do is we need to give a target value to the right side in order to calculate it. That's the key. It's not that we're going to loop through an unordered map on the right side after it's finished computing. We're actually going to loop through all the possibilities that we have on the left side. If we're adding, then we're going to decrement the target by that added value, and then recursively compute with that new target value on the right side, and only get the strings that satisfy that what we're looking for, and then combine them. And similarly for subtraction, same deal. And the recursion is just going to be, again, take some from left to right, some portion of a multiplicative, all the multiplicative terms from left to right, or for some number. You're going to loop over each index, and then again, you were already given a target number, so then you subtract for each of those, subtract again, and then process recursively again. So that should work. It's just, I don't know how much redundant work we're going to end up doing. That's one thing. I'm not sure if it's more redundant to process everything on the right side. See, the problem with that is that it's hard to figure out like where you should, like you could split things, but it's just there are a lot of I think there's a lot of redundancy either way. I don't know, it's hard to tell. But there's at least two different ways we could optimize. One is we can push forward the next target based off of what terms we can have on the left side. Do it that way, or we can don't push anything forward, just recurse full stop on the right side, and then from all of the results that are possible on the right side, we can figure out which ones, sift through which ones we want based off whether we select an addition or subtraction. The tricky thing about the second approach, I'm not entirely sure how to code that because I guess what you'd end up doing is that at each, like you select some spot and you split, and then you on the right side you recurse on the right side. Once you do that, I'm trying to think what the base cases look like, things like that. You're going to collect all of the, on the right side, you're actually going to just collect all of the, that one's a little bit harder. I think the first one I described is a little bit easier to actually code. The second one is a little more involved because you want to do kind of something similar to what I just did, where you take all the possible multiplication parts that you could have, and then for each of those, check to see if you have what you're looking for in the right side recursion, and return that. And the right side recursion will also select an addition or subtraction for some part, and yeah, I guess all of you gather up all of the results that work. I guess the base case is just if you get to a portion that's if you get to a portion that's already been computed, where one of the multiplicative terms is exactly the target, then you can use that. So that's kind of the base case. And that would be a solution. That's pretty much, and you would do that, I think, at the top of the base case. You just say if this section, this target you're looking for is somewhere in the set of multiplicative terms for this range, then you're done. You actually wouldn't be done. You would actually, the base case, that's not the base case. That's actually just, you would add those values to the result set. But actually, because you could further break down that section into things that are not necessarily multiplicative terms. But you would have a base case where once your range is, you actually don't even need to do that. I think you'll just naturally have what you need. If you if your result set is empty, then obviously it'll terminate early automatically. But you don't need to go all the way to you don't need to go like there aren't any like basically you're just going to process like whatever's left over, quote unquote. And actually, you don't even really need a base case in that regard. Just start with empty sets of things, empty maps, I guess. And so there's just nothing in the returned map. Then you don't have your loop just doesn't loop over anything recursively. Yeah. So there's at least two approaches. One is to give the look ahead each time, give the target each time, and try to make that target. Another approach is to loop through everything without that target changing, and then after you've grabbed everything, then check in your unordered set. I think it's actually unordered map. I think it's actually easier to I think it's easier to actually provide the look ahead the target ahead of time. If you can get all possible combinations like 1, 2, 3, 4, 1 plus 2 plus 3, let me post the problem for you so you don't need to guess. Let me know if you can click that link. Not able to read the full problem. I understand it's not character by character, but can be considered any number inside the string. Yeah, exactly. Try the first phase. First step should be 1, 2, 4, 5, 6. Greater than vec equals 1, vec 0 equals 1, vec 1 equals 2. Vec 6 equals 12, vec 7 equals 24. Oh, yeah, interesting. The first phase is a little complicated. Yeah, I think I was just explaining that. Also, I realized that was 7 minutes ago that you responded. Yeah, the first phase is kind of not too complicated, but somewhat involved. I mean, that I actually already got, I think. I already got it. But the second part is kind of involved. Like I said, I think what I'm going to go with is what I was just describing, where I do it recursively, and we're going to provide the target and try to do it that way. So let's see if we can do this. Alrighty, so we'll say just recurse. It's not really a DFS anymore, it's just recursion. This probably could be converted to a DP also relatively easily. I'm not sure, maybe, but I don't know. So, okay, so we're gonna have all of our, we have all these things that we want to provide to as for context. So we have the skip, we have result, or not result, array, we have possible multi, all these things I think we'll end up using, possibly using array S, potentially end up using. We're going to call our recursion. We have also call it F. We have a range. We'll have A and B for the range. So we want to recurse on 0 to n minus 1. And oops, and recurse is going to be F. Yeah. So I don't even know what this is going to return. We were saying, oh, and we have a target that we send forward, and we were saying, so there's going to be a return value each time, and we're saying we want this to be this I think should also be an unordered map of strings. I think that's the correct way to do this. Maybe, I'm actually not sure. And so we won't have ret, we'll say base cases, or base case. So if target is in, so if we can, yeah, if the target is any of the multiplicative portions, then we want to add those. And we just say doesn't return, doesn't exit processing. I would just call it base case, it's fine. So the way this is going to work is if the target is equal to, it's not just if it's equal, if it's one of the, if it's one of the possible multi-keys, then we're going to add to ret, we're going to say ret of the target is going to be an unordered set. We're going to insert into that set possible multi of, so this is another set, so we're actually going to, it's not just insert, we're going to say, we're going to update this set, so we're going to use some of this syntax, of possible multi-target. Yeah, so we're going to add all the strings to this result is going to be this target, and when we get all those strings recursively, we're going to combine them at the top level. So we don't do it here, the combination, but at the end we'll do the combination, so the recursive part. And it's not going to be recursive F, it's going to be recursive, just recurse here. Now we're going to say, so add and subtract. We're going to say for int I equals a, I plus 1 is less than b, less than or equal to b, increment I. So we're going to do something very similar to what we did above here, where we pick a split point between I and A and B, right? That's where we're going to insert, there's going to be at least one value to consider on the left and the right sides. So we're going to split them into left and right sides. And we're going to say, actually the adding and subtracting are going to be in both parts, both inside here. And so we say, so we have possible multi, so the left side is going to be the multiplicative term. So possible multi, we're going to process on the left side. But on the right side, left is going to be possible multi of, it's going to be A to I, right? And right, and this is going to be the same for both of these. And the right side is going to be not possible multi of AI, but it's going to be recursion F of I plus 1 to B. And we're saying also we want, this is just, I guess this is going to return the same thing as this possible multi. This could be type deft. I think that would be a good idea to type deft that. So we have a left and a right side recursively. So recursively get a right side. Our left side comes from what we've already generated previously. We're going to say, and we have a target value. So the target is our initial target. This target value is going to be, depends on, the right side will be add right and subtract right. So we say add right and subtract right. So the target, if we are going to add these two things together, that means our target is going to be minus whatever key we have. So we have to do for each key, so I say auto P, and now this is possible multi is a map, so it's going to be for each map, or not map, let's just say M for map, of the possible of left. We're going to say int const int v equals m, or we should really, these are, yeah, this is a map. In the unordered map you have pairs, so it's actually going to be p dot first, and you're going to say target minus v if you're adding, and if you're subtracting, it's going to be plus v, right? So these are how the targets change as we process the possible multi-side, what we could have on the left side. And so add right, add sub right. For each of these, what you're going to do is you're going to do a similar process that we did up here, almost the same kind of routine where you combine. So it's going to say there's left, there's right, and we say for each pair in the left side, which we already have that, say each pair in the right side, we could say P1, P2, that's fine. So this new value is, it should be the target, actually. The value will already be the target that we're looking for, so we don't need that. We have the strings of our left side are going to be combined with the strings of the right side, and these strings are going to be, and we're going to insert those into, it's going to be the target, and it's going to be ret of target. Now that's kind of interesting. I think we, yeah, that's a little weird. I don't know if we actually need this target anymore because we already know what the target's going to be. So what we return on the right side doesn't actually need to have an unordered map associated with it. It can actually just be unordered set of strings. I think that's fine. So let's try that. See how that works out. So we have the left side, we have the right side. Oh, my neck. We don't really need a target anymore. We can just say insert into this set that we're going to return. And this is, we said this is addition, right? So we're going to add on the right side. We add the left strings, the right strings. All right, because we're giving this target already. P1 first, P2 is right, and the right side, it's actually, they're not strings anymore on the right side. They're just, I mean, they're not, it's not a pair of things anymore. It's a, these are just strings. We can call them like S2 on the right side. And now we can say, oh yeah, that simplifies things a lot, huh? We can say S2 or S1 is, oh, for that pair, P1.second, and now you could say S1 plus S2 for each of the things on the right side. And you also can do this for the right side again. So add right, so subtracting right and adding right are slightly different. These are the same ideas. Now this we want to memoize probably, I think, and we can add that. So we do have a regular map we can use. We're going to memoize this. Now I don't know if this will actually help us, but it might. So the results, so map of, for an integer, we have int. I don't think it actually helps us to memoize at all. And the reason is these target values are going to be different every time we execute this, so there's no reason to memoize. I take it back. I was going to say that one of the reasons why this is such a tricky problem is that it's hard to figure out a way to memoize this properly. Okay, so now we call f with a, b in our target and f. On the right side, this is I plus 1 to b. We have possible multi. We operate all over the possible multiplications. And then we return ret. So I think that's it. It's relatively straightforward. From there, we actually just have we use an unordered set of strings, but we can actually just return. So we can say auto like ret equals this at the end of it, and or result. I like to use result or intermediary results. And then you can return standard vector of strings of result.begin and result.end. And let's see how that goes. Undeclared identifier possible multi. Did you mean possible mult? Yes, I did. And I guess I don't need these three at all. May not, I don't know. We might need them. Who knows? Oh wow, I used that wrong variable so many places. How are we doing on time? Yeah, we're like hours into this. I don't know if we need these. I don't think we do. I can get rid of those. Where's the issue? Oh, yeah. Multiples. It's gonna be A and B. Could just use a reference here. Yeah, I missed that part. Oh, okay, never mind. Doesn't really matter. I don't need that extra portion. This is A and B, and this is A and B. Does not provide, oh yeah, we said we can get rid of that, right? Sweet. No viable overloaded. What do you mean? Oh, because these are unordered sets rather than, I see. I see the problem. Okay, that's fine. Yeah, because it's not, they're unordered sets, so you don't have that overload. Phase 1 was easy. I've now listed all possible numbers for calculation. Oh. Really? Oh, but you're gonna do. Oh, phase one. Oh, you did. Okay. Very good. Very good. Oh. Declaration of variable left with the deuce type auto requires initializer. I think it's supposed to be this way. That might be the issue. I don't know. I did that so many times. Oh, very good that you have the initializer. Very good. Or you have the what am I doing? I got something going on here. 1, 2, 3, 4, 5, 6. List, new list. Substring, parse. C#. Yeah, I see that. Oh, I see. So you got all of the integers. Oh, very good. Oh yeah. Oh, I see. Oh, I'm sorry. I didn't realize this is phase one, and then this is phase two, and then this is phase three. Yes. I didn't realize it. Right. Because you're talking about phase one all the way up there. Ah, gotcha. Yeah, it's not too bad. Now you got to be careful though, because part of the issue is the associated substring with that particular number. It's a little bit. I mean, it depends on how you do it, but the awkward thing is that you actually don't want to use, like, if you had 000, for instance, as a substring, you don't want to use the 0 associated with those 000s, again, depending on how you do it, because those 000s aren't supposed to be processed at all in the final evaluation. So that's something I should mention. The way I handled that was I added just a skip boolean associated with that particular sequence. So if that sequence has a leading 0, then the skip gets set to true, and we don't do the other processing. But if otherwise, in all the other cases though, the skip would be set to false. So that way I would know later on if a certain range should be skipped. What happened here? Oh, I think we can't convert to a const because, oh, look at that, unordered set string hash equal to. So what's interesting is these are, so I said P1, we could call it P. P first is, oh, I'm wrong. This is a set. This is a set of strings. Oh, okay, I did do this wrong. Yeah, all right. I did do this wrong. So really this is an unordered set of strings. Not just a single string. I see. So it's going to be p.second that we need to do here. All right, I was going to say, I felt like this was just a little too less complicated than it should be. You can imagine that. Not as complicated as it should be. And also this is an add right and sub right. No longer. Yeah, I see. I think this is what we need, something like this. How about this? What happens if we do this? You're way ahead. I guess so, yeah. Also, I've been doing this for like three days now, so there's that. There's that. Cannot bind to a temporary of type unordered set. What? Oh, alright. It's fine. Non-const L value reference to type unordered set. Cannot bind to a temporary of unordered set. Oh, okay. Okay, sure. Alright, wrong? But what? Oh, that's interesting. So our second output's close. Let's see. They're both wrong though. They're both quite wrong. All right. Oh, well, that's probably why. I forgot the subtraction is supposed to look like that. That could have something to do with it. Although, I don't think so. Let's go to, that was fast though. That was really fast. It's 28 milliseconds, so that was very quick. Let's get rid of all the debug information here. Printing. Start with that. So that'd be really good if this is quick. But we're not getting any output for the first one. And the second one, I think we have too much output. Yeah, we're not actually supposed to go that far. Oh no, it's fine. I think we might be correct on the second one. Let's try that. See what happens on the second one. Let's see. That'd be nice. That would be nice. Wrong. Shoot. Oh man. They're expecting a lot more than what we have. So I did something wrong. Whoa. Okay, that's the first one. And the second one. Oh man, okay, so we... Interesting. So this is what they expect. It's here. They're expecting way less than I output. Does that mean I have multiples? I don't think so. Oh man, look at this. How did how did we get this? What is this? What's the target? Is it 100? 44 times 35 is way more than 100. This is huge. What is this? What's that? What? The minus will blow everything because you cannot make a wall and reduce the number of combinations. Oh, is that what it is? Are you sure? These will just be empty if it doesn't fit. It doesn't work. But my question is, how did I get 35 times 44 is somewhere close to 100? 1540? That's way off. So, oh, I see. Yeah, all of these strings will be added for that target. You update your target, right? So AB target minus V. If we're gonna add S2, whatever we get for that, recursively. And then on the left side, whatever we get for that, on the right, if we add V, subtracting. So this minus this A, let's say X minus Y equals target. X minus Y equals target means that Y is equal to, oh, I did this wrong. I think it's V minus target. I think that's what it's supposed to be. You have X plus Y equals target, means Y is target minus X. X minus Y equals target means Y is X minus target. Yeah. Yes. That's more accurate, but still wrong. Or hopefully more accurate, I don't know. Oh, man. Like, where did this one come from? For example, how did we get this? 1 times 2 plus 34. Oh, it might be correct. Plus 34 plus 43 plus 5 plus 6 plus 4. Oh, man, that's super close. Wait, is that right? 2 plus 34 plus 43 plus 5 plus 6 plus 4 plus 5. Uh-oh, this is 99. How did we get 99? Oh no. Wait a minute, why did we get 99? How did that happen? No. What? What? I don't know. What? Where did we get 99? No. So 1 times 2 is one of the multiplicative terms. Oh, you know what it might be? It might be the... This part might not be correct. So... Oh, that's what... Oh, but... These are longs, not ints, by the way. That's what's wrong. This really should be a type def int to strings map long to strings map. That's why. It's kind of a minor error. Those need to be longs. Not ints. Not ints. And these should be longs too, the targets. Okay, what happens if we do this? Oh, probably some compiler error. Oh, yeah. I probably missed something somewhere, but let's see. Okay. Let's see if that's a little bit better than what we had before. I see the issue is that, yeah, my, my multiplicative terms were not correct at all. Oh, that's a lot better. Okay. That's a lot smaller. Okay, let's go for some of the smaller test cases here. Yeah, let's go for these example test cases, because you'll see the problems a lot easier in the smaller test cases. Oh. In type int. Right, but these are both longs. Oh. That's why. I see the problem. See the problem. Hey, oh, it works. Wow. Oh, no kidding. Oh. Okay. So what's going on wrong with this one? It's pretty sweet that that works too, by the way. That's encouraging. All right, so something's wrong here. This one. Oh. Okay. Pretty good. And what is this one? Oh. They look the same. What's wrong? These two are not the same. And that was really fast. That was 19 milliseconds. That was extremely fast. Hey, 20 milliseconds. Okay, but now the question is, what is the matter? Yeah, if I had a question like this during an interview, I would be just absolutely destroyed. There would be no way I could solve this. Okay, can we get a diff? What's different? So the first one maybe might be wrong, right? Minus 45. So 1 times 2 times 3 times 4 times 4. Okay, okay. 4 factorial I think is 24. So 24 times 4 minus 35 plus 6 minus 45. Okay. That is nowhere near. It's nowhere near 100. How did that happen? What? Well, it's good that it's fast, but it's wrong. It's not easy from now. Yeah, after those parts, those two parts that we did were relatively easy, but this part's hard. All right, 16 times 6 gives us 96. Minus 35 plus 6 minus 45. All right, we're at 22 instead of 100. What? Where did I get this from? How did that happen? Huh? It does properly use the whole array, but that's not supposed to happen. How did this happen? Huh? Where's the chain of events to make this happen? Also this one's crazy. If you do 23 times 16, whoa. These are so wrong. Minus 3 minus 5 minus 6 times 45. That's 90. That's nowhere near 100. What? Where are these coming from? How did this happen? Priority in multiplication than sum? Sorry about English. Yeah, multiplication takes priority over sums. It's true. But we already addressed that. That's actually what we did. We already did that. We did the multiplications first. And so in each case all of these are separated by additions and subtractions, so we're never actually going to combine all the multiplicative terms we're going to do first. Yeah, so I wonder, maybe you're right, it could have something to do with it. I could be wrong. It could be that we need to do yeah, actually you're right. No, this still doesn't work properly because when we subtract, for instance, because we're going left to right, all of the, yeah, I see the problem. Because we're going left to right, that's why. Oh, this is so awkward. So we're gonna go right to left. We're gonna go top down. So the issue is something like this. You're actually right about that. It's not exactly the issue. It's just that we're still going. I'm going in the wrong direction. So if you look carefully here, if you do 6 minus 45. So watch this. 6 minus 45. No, sorry. If you do this whole expression minus this entire expression, then it works, or it should work. Oh no, is that? How does this? I don't know. I don't know what's going on here. I actually don't know. 2 times 3 times 4 minus. Wait. 1. So it's 4 factorial times 4 minus this expression on the right, which is negative 35 plus 6 minus 45. Right, and, or sorry, I did it wrong. What do you say? It's, if you do 6 minus 45, you add that to 35, and then you subtract this, or negate it, and add that to 96, that gives you 100. I did that wrong. But yeah, basically, if you did the order of operations right to left, then it would work. That's the problem. So if you do 6 minus 45, then you do 35 plus 39, or negative 39, gives you negative 4. Then you're going to subtract that, so you negate it, right? And then add that to the thing on the left, which is 4 times 4 factorial. That gives you 100. Yeah, that's why. It's because we're doing right to left instead of left to right. That's kind of a subtle thing, but if we fix that, I think we'll be done if we fix it. Just means we need to go right to left instead of left to right, which would be very similar. Start with. Actually, the range is the same. It's just this goes from B to A, really. And you go, I starts from B, and you just have to say I minus 1 is greater than or equal to A. And so the right side is going to be from something to B, I think I to B, and then the left side so subtracting on the left side is confusing, and subtracting on the and adding on the left side. Adding on the left side works out okay, but subtracting on the left side is awkward. This is going to be from A to not to B but to I. So it's A to, it should be I minus 1. So it doesn't include I. So yeah, because B includes, B is included with I, or wherever I ends. Yeah, so it's going to be A to I minus 1 and I to B. These are still going to be similar. They're not exactly the same. So sub left, sub right. So add right, add left, and add right, sub left. And now what you're going to do is, when you're adding the left side, the addition doesn't matter, but subtracting is a little confusing because you're going to subtract to actually what you currently have. So you have x plus y is equal to the target. The y is now on the right side, which is v. X is then target minus v, which that's confusing. And then I guess these swap. So what you end up with is if x plus y equals, call it alpha, and then an x is the left and y is the right. Now we're looking for the left side, so x is going to be alpha minus y, which is that's this one. I'm so confused. I have to think about this. Let's say you have x plus y, you have y, you're looking for x plus y is equal to alpha. That means x is equal to target minus as alpha minus y. X is alpha minus y. And we have y. Yeah, y is v. So alpha minus y is v. X minus y equals alpha, and we're looking for x, then y, yeah, you add, x is then alpha plus y. X minus, yeah, then x is alpha plus y. Okay, I think that's what I had before. Now, I don't know if this is going to work. I don't know if this is even going to compile. This might, let's see. And this is, oh, wait. Right, HP, yes, that's correct. Identifier X. Oh, it's V. X minus Y equals alpha, alpha plus Y equals X, yeah, okay. But now this is just wrong. No. Oh, it goes the other way around now, by the way. For each string in P second is now the right side and left is the, you gotta swap these two. I think that's the issue. I think we're almost there. Something like this. Hopefully, maybe, let's see. Hey, we got it. Whew, 20 milliseconds. That's a lot faster than we had before. Sweet. Are we done? That's the question. Did we do it? Maybe, hopefully, I don't know. Find out. Do lots of testing. Hey, that looks good. All right, do I have the right, it's part 4. I think we solved it. I'm gonna say we solved it. Hard solved, C++. Okay. Are you still with me, Mr. MGTOW Wolf? Aha, you did it. Thank you. Yeah. Hey, hey. Dude, I was not a happy camper working on this problem. I'm gonna give it an upvote. Being challenged is good. Being challenged is good. I was doing a lot of complaining. I was in a grumpy mood and I was doing a lot of complaining, but I think we got it. I think that's all we needed to do. Yeah. There are a few different different cases to look at. So we said this one before. Let's try some of these challenging test cases. How many zeros we have? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. So we have 8, 9, 10. Yeah, it should be this one. Okay. That's encouraging. That's encouraging. Congrats. Thank you. Thank you. Yeah. The runtime on this is, I don't even know. It's kind of wild. But it worked out. I don't know, dude. I have no idea how to evaluate like this algorithm. This is definitely way better than the first one I had. This is not easy to code though. I would say figuring this out and coding it, like in a 45-minute interview would be pretty much impossible for me to do. I would say that's probably fair to say. So it's kind of involved. Something of a mess. So maybe we can get, now I'm tempted to try, I mean, we could just try like a bunch of different test cases, you know. I don't know. Just try different things, see what happens. See if we get any issues. So we're not TLE, which is good. We're mostly correct, which is good. We're able to handle the leading zeros, which is good. We're not failing on, because we're using longs for everything, so we're not failing on integer overflows or anything like that. What else can I think of that we could test before we submit this? I don't know. No zeros. We have addition, subtraction, multiplication. Oh yeah, we could try like multiple zeros. Try that. See what happens when we do that. That's a really tricky edge case. It's a very complex code. Yeah. Yeah. That's putting it lightly. There's a lot going on here. Oh, we got that one too. Sweet. All right. All right, I'm gonna go for it. There's always something I missed. Hey, we got it. We're better than 92%. Oh, that's satisfying. There we go. That feels good. That feels good. I usually am not that fast when it comes to oh, did it. Okay, that actually feels really good. That actually feels really good. I thought I was gonna be like whatever about this when I finally got it, but it actually feels really good. Pretty good on the memory and the speed. That's good. That's good. All right, I'll take it. I'll take it. But yeah, I got like multiple wrong answers, multiple time limits succeeded. Look at, I didn't even submit till yesterday, but I was working on it. It's like the third day I think I was working on it now, fourth day maybe. 4 parts I think usually means 4 days. Let me see if I can explain this. So yeah, we're like almost 90%. We rolled the first time we got 92%. It's pretty good. So the way this works, I think if we might be able to do this. This is a tricky thing, but we might be able to switch from sets to strings. That could be a possibility. The only reason why I wouldn't want to do that is because, or not sets, to like something that's not hashed, to like vectors. The only reason I don't want to do that, though, and then we don't have to do this extra step at the bottom, but the reason I don't want to do that is because of, I think it's possible to get a left side and a right side that, that the 2 parts are unique, but when you combine them, they're not unique anymore. So you could have like 1 + 1 + 1 + 1. So, but then, no, there's no way to get, I don't know. I don't think you can, I don't think so. I'm wondering. Can I change this to a vector? Very curious to see if this still works. I don't know. We're going to find out now. Because I think it'll be a little faster if we use a vector. As opposed to let's find out. I'll try to explain the code too in a minute. If this works, I'll explain it. Oh, it still works. Whoa. No. No kidding. Really? Wow. Does it? Ooh, that's nice. That's all. That's that makes things a little bit easier. Oh, look at that. I wasn't sure about that. That's why I was using a oh. Oh, wait, that's slow now. But that was just 3 times slow. Wait, what happened? There you go. Okay. I was gonna say, I was like, that was just like randomly 3 times slower. Okay. That speeds up things a little bit. And then now here's another. This is a hard one. Whether or not these need to be unordered sets. That's a really tricky one. Let's see if we make these vectors instead of sets. I'm gonna comment it out instead of totally deleting it. Okay. Same thing here. I don't know what the runtime of this is, by the way. I think it's no, this might not be correct. Okay, no, it's not. All right. Yeah. Yeah, you need to use. So, okay, that's interesting. Okay, that's fine. Yeah, so this second step, for some reason, you need to use a set. And the reason why you need a set is not really that obvious. Why do you need a set for this? That's something to ponder. Let's think about that for a minute. So that means that somehow when you're looking at combinations of multiplicative strings, the left string and the right string, when you combine them, you can get a string that you already have in the... Yeah, I think that makes sense, because if you have like 1 times 1, or... yes, you can do it. Yeah, okay, I got it. You could have 1 times 1 times 1 times 1. So you have 4 ones. On the left side, you have 3 ones multiplied. On the right side, you have 1 multiplied. That could give you the same string as 2 ones multiplied on the left and 2 ones multiplied on the right. That's why you got to use an unordered set. But you won't have the same thing for these. And can I prove that? Can I prove you won't get the same thing? Yeah, I think so, because you're not going to, because the left and right sides are the left sides are always multiplicative, and the right sides, and you're combining multiplicative pieces between additions and subtractions. So you can never get a final result that's not unique. Yeah, I think it works. The mechanics of it is just different. I think that's why it's hard to express why you can't do the same trick here. Why you do need to use an unordered set. It definitely makes sense why you definitely would need to use an unordered set here. I get that. You can come up with a counter example for that. But why you wouldn't push back might take longer. No, I don't think so. It's just kind of random how it operates. Like if it'll be faster or slower. Oh, there you go. Beautiful. Look at that. 88. I like that. Yeah, that was like the first one. Yeah, I like that. It's good. Apparently, there's a faster way to do this, by the way, which is interesting. I think if I didn't recurse, it could be faster. That might be it, because I don't actually have to recurse. This could be a DP solution. Definitely could be a DP solution. That might be actually the way to make this the 100% is to make this a DP solution. The issue is I'm just submitting it a ton of times because this takes my score down so much by submitting 7 wrong answers. I have to submit 80 correct answers, or 70. Yeah, I have to submit. How does it work? It's 9. I have to submit 63 correct answers in order to get the same score that I had to get 90% now for my score. So yeah. I think the reason, yeah, so it's obvious why you need the set here, but it's not so obvious why you don't need the set here. And I think the reason is, I think the reason is that the strings, you could basically always prove the strings that you're going to get when you find the left and right sides will always be unique. And how do you prove that? Well, for starters, for a given addition and subtraction symbol, right? For starters, you know that the left side and the right side, well, actually, it's inductive. So if the left side and the right side are both unique, then when you combine them across the addition symbol, then that entire string is guaranteed to be unique, right? Unless the left side and the right side. Now, even if the left side and the right side were mirrors of each other, yeah, I guess what's weird here is that you for some reason you don't get like 1 plus like 4 ones added across. How come that doesn't happen? And the reason for that is because this is going left to right. That means that you can only have a 1 on the left, or excuse me, it's going right to left. You can only have a 1 on the right and 3 ones on the left. You're never going to have 1 plus 1 on the right. That's why. The reason is because these are multiplicative terms only. So adding addition symbols in between means that you only have multiplicative terms on the right side each time. So adding these addition symbols each time, I actually don't know, man. I can't figure it out. It feels like, yeah, if the left and the right are unique, that's it. I mean, you can't, because they necessarily have different symbols. Yeah, I think that's why. It's because you can guarantee that the something on the left side, if it's the only time, no, because they're different symbols. Yeah, because you're adding unique multiplicative symbols, you're combining across an additive. I don't know, man. It's hard to prove that. That's hard to prove. That's a tricky one. That's a really tricky one. Prove why you don't need a set here, but you do need a set on the other side. I'm gonna hit this button a few more times. That's like a really challenging one to prove. That this will still be correct, even after you don't use a set. Yeah, that's challenging. That's challenging. Well, we're gonna hit the button one more time, and then just be grateful that we made it. Oh, there we go. Oof, 72 milliseconds. Beautiful. It's 92, almost 93%. What we're looking for is the left side and the right side. How do we prove that it's unique across the additions and subtraction symbols? Well, obviously they don't interfere with each other. That's one thing, right? Because they have a different symbol. The add and subtract symbols are different. The symbols on the right, we know those are multiplicative only. So the left side needs to be strictly multiplicative in order to, so you'd have to have a right pair and a left pair that are the same. But because, or you have to have the results of, you have to have some alpha prime and beta prime. When you put a plus symbol between them, that concatenation is equal to some alpha plus beta. Where, now we know, yeah, that has to happen somehow. And we were saying it's only at the end, potentially, at the end of the recursion. Well, at the end of the recursion, you have some arbitrary sequence of additions, subtractions, multiplications on the left side, but the right side is only multiplicative terms. And we can guarantee the right side is unique. We can maybe inductively show that the left side is unique. Let's just suppose that the left side is unique inductively. So alpha and alpha prime are not going to be the same, and beta prime are not going to be the same. Well, if alpha prime plus beta prime is equal to alpha plus beta, since the plus signs are equal, that means that the only way for that to be equal is that the left side is equal and the right side is equal. Or somehow concatenating these would be equal. But the problem is that since you don't have any plus signs on the right side, because you could have some, like, basically, in order for these to be equal, you could split, let's say, beta into two pieces where alpha prime is a substring of like alpha plus beta 1, and then there's a plus beta 2, right? And so then alpha prime is equal to that, and then the pluses are equal, and then beta 2 is equal to beta prime. You could have something like that. That's possible, but since there's no plus signs on the right, you cannot break down beta such that you can do that. So such that you can create a substring where these could be equal to each other. I think that's the crux of it, is that if they were equal, that would imply that there's more than one plus sign on the right side. It would be necessary for one or the other. You'd have to somehow make either alpha prime a substring or alpha a substring of the other string, where if alpha is the substring, then beta prime was split, and if alpha prime is the substring, then beta would be split. But that both of those cases require an extra plus sign on the right side, which would be a contradiction. So because these are unique, now you could argue maybe you could have the substring can go the other way, that there's a plus sign from right to left. So there's an extra plus sign on the alpha prime or alpha side, but again, the substringing the other direction too doesn't work, because beta prime and beta are both of them don't have a plus sign in them, so it's impossible for those to be substrings of each other with pluses in between as well. I think that's the rationale. I think that's how you prove it, that alpha prime, beta prime, alpha and beta, that if you concatenate those with a plus sign in between, alpha prime plus beta prime can't be equal to alpha plus beta. If you can guarantee that a plus symbol never occurs in beta prime and beta, and inductively that you can show that those are unique with respect to each other, and alpha and alpha prime are unique with respect to each other. That is wild. I think that's true. Yeah, that's amazing. Whoa. Can't think of any counterexamples, but I think that's the proof. Is that sufficient proof, though? It seems like it might not be good enough. I don't know if logically that holds. alpha and alpha prime, beta, beta prime. Yeah, I think so. In order for these things to be equal, then it must be the case that you have a substring one way or the other that consumes a plus sign on the right side, or implies a plus sign on the right side on beta or in beta or beta prime. I think in all possible scenarios you must have that in order to say that these are equal, knowing that alpha is not equal to alpha prime and beta is not equal to beta prime. Yeah, you necessarily would need to cross the plus sign on alpha or alpha prime, or beta and beta prime going the other direction. I think that's the way to express it. It's kind of tricky to express that, but that's what that would be the reasoning, I think, and then that gives you inductive hypothesis that they're not equal. Wow, or that they're that proves the uniqueness. Dude, that is great. Or not great, but that's good. I like that. I'm grateful. All right, I'm gonna go. Pretty interesting. We got it. We did it. Praise God, man. Just praise God for everything. Praise God for everything. Praise God for forgiving my sins, an evil and wicked sinner, and for saving my soul, for sending Jesus Christ to die on the cross. Bad news that I'm a hell-bound sinner, and the good news that if I repent and believe and be made a new creature in Christ, I can be born again. I can have everlasting life in Christ. But so let me explain the solution, by the way. And I do think there is yet another, as I said, there's one more optimization here by not doing this recursively. And it's not going to make it that much faster. I don't know if it'll really be that much of a solution. Or a couple things, maybe two possible small updates. So one, you could do this dynamic programming style, and that would be quite a bit faster. Actually, I don't know if it'll be faster. Maybe it might be faster. Hopefully, it'll be faster. And then the other thing to do is to update. You can use. This could be a struct. I don't know if those will make things faster, but this could be a struct instead of 3 separate items, and that'll simplify the code a bit. I actually don't know if that'll make it any faster. But yeah, so I'm actually slow it down a bit. I actually don't know how to optimize this beyond this. So let me explain what we're doing. First iteration, we talked about, we are figuring out. We're basically taking each sub range. There's a quadratic number of them, so 100 of them at most. Taking each of those and breaking them into. We're calculating 3 things. 1, whether it should be skipped. So if it has a leading 0, we're going to skip it. 2, what the integer value would be. So we're going to convert, if we take the substring and convert that to an integer, right? That's the S2L here. And then the third thing we're calculating is the substring itself. So we're taking that substring. So we're going to, for each possible range, I and j, or all the ranges that we can have, we're going to take the substring, check whether or not it has a leading 0, and set the skip variable or not, depending on whether or not it has a leading 0. And also calculate the integer that's represented by that substring. So we do that first preprocessing step. Pretty straightforward, pretty simple. Second preprocessing step is a little bit involved. What we're going to do is we're going to have an array for each range. The data we're going to get is all of the multiplicative integers that can be created, the long values, and we're going to create a map of all the strings that can get us a particular integer. We're going to map that, use that as the key, that integer as the key, and take all the strings that give us that. We're going to put those into an unordered set of strings. So we have all the different possible ways you can add the multiplication sign in between inside of a subrange, and all the different numbers that result from all those multiplications. And then for each of those numbers, we're going to collect all of the ways that we could generate those strings to create those numbers as an unordered set of those strings. So for instance, if there's multiple ways to get to 2 or 4, which would be like 1 times 1 times 4, and 2 times 2 times 1, and 1 times 2 times 1, and all that stuff in a particular range, or 1 times 2 times 1. Well, those wouldn't really work, but there might be many ways to actually get a particular number. So we have an unordered set of all the strings to get that particular number. So we get all the numbers in a range that we could multiply to get, and we also attach to those numbers all of the strings associated with that would generate that number. And this is pretty involved. As I said, this is related to Catalan numbers. This is in our use cases, we only have at most like 17,000 of these, and I think you kind of increase that number slightly because we're calculating this for every possible range, and there's a quadratic number of ranges. The largest single range would be at most 17,000, roughly 17,000, but there's there's 100 of them, right? If 10 squared is 100, so there would be 100 of these ranges. Some of them a lot smaller than others, some of them a lot larger, but they are combinatorial in size, so a very large number potentially, and that's also one of the reasons why this algorithm, even though it's fast enough to meet the standard they've set here, it's not fast enough in general, because this is always going to be, this calculation right here is always going to be it's always going to be combinatorial in nature, meaning it's going to be it's always going to be combinatorial in nature, meaning it's going to be extremely expensive as the set of characters that working with increases. So yeah, but yeah, this is a very efficient way to figure out what all the possible multiplicative numbers could be, or is efficient for this problem, and it's kind of involved because you're both calculating the numbers and the strings and associating the strings to the numbers. It's not too hard to figure out what's going on with that explanation, but it's also a dynamic programming solution too. So it has three loops going on here, but obviously these loops inside are quite involved. This is kind of the part where it would be combinatorial, because you've just got 1, 2, 3 outer loops would be cubic, and then these 1, 2, 3, 4 inner loops inside of 3 outer loops gives you 7 loops, which is a lot. That's a lot of looping. This is the part that makes it sort of Catalan. All right, anyway, so now you have the recursion. Now this is just, we're going right to left, and all we're doing is we're saying, okay, on the right side, we're going to look at all the possible multiplicative terms we could have, and for a certain range. And then we're going to say on the left side, we're going to recurse. We're going to say the left side is going to return a set of, or a vector of strings for a possible target, and on the right side we're going to take all of the possible multiplicative terms that we can get, take our target, subtract the number associated with that multiplicative term, and each of those terms has, as we mentioned, a whole set of strings that will get you to that target value, and then you just combine with an addition or a subtraction, recursing on the left side, where you'll get on the left side you'll have, and we did the math, it's either target minus v or target plus v. So either if you're going to add, you're going to your new target on the left side is going to be the previous target minus the part on the right for the adding, and then and subtracting, it's going to be the part on the left. It needs to be the original target plus the part we're going to subtract from the right side. So that's sort of target plus v in our code. And then you loop over all of the strings and combine them in every possible way. So that's why you have the double loop. That's for each element on the left side, you're going to take one of the elements on the right side and combine. Where the right side, these are all the different ways you can get to a certain value y, and on the left side, all the different ways you can get to a certain value x. And so x plus y, all the ways you can get to x plus y are all the looping over all the left sides and the right sides and combining them with either an addition or subtraction in the middle. So that's what's going on here. We can do this recursively, and we also, only on the right side, we only select from the possible multiplicative terms. So that way what we're doing is we're adding and subtracting only the multiplicative terms at each point. What this does for us is, one, it splits the problem up in a way that's easy to understand, And two, it also allows us to just do a simple right to left parsing, basically. And again, I mentioned this could be done using dynamic programming if you wanted to, or really not even dynamic programming, just like a simple loop, really. Because you would just process the addition part and the subtraction part in one piece, update your return vector that you have, and then keep going. So yeah, you could actually do this right to left. I mean, it's a little easier to do this recursively, I think. I'm thinking about it, but I'm pretty sure you could do this using a dynamic programming approach as well, right to left, and that's simple enough. Or it would actually be left to right. How would that work? It would be, yeah, I'm actually not sure how you do the DV part. It's a little weird because you need the whole left side to be done before you process the right side, but you do want to start on the right side. So that's confusing. I guess what you'd have to do is actually, the right range would be very large initially, and the left side would be small. And I don't actually know how you do it. I'd have to think about that for a while, because you'd have to you want to break this up into, I think also, by the way, you could make this iterative, but you want to use the right side, but you want to pair it up with all of the possibilities for the left side, or any of the possibilities on the left side. So, but you also want to generate the possibilities for the left side, like, I guess iteratively. In other words, have multiple addition symbols and subtraction symbols on the left side. How does that work? It would be, so you would have to process left to right to generate those values, but the processing itself would have to use a right range. Yeah, I think that's fine. I think you can process the left side with a very large right multiplicative term, and then when you process the next range, it's going to be both. It could be both something from, it could be anything from what you've already processed up to that point. Does that make sense? It could be anything from the multiplicative portion on the left side, or I don't know how I would do this exactly with, because also the target value makes things complicated. Yeah, I don't know how I would do this if I wasn't doing it recursively. It's definitely a lot easier to think through if it's recursive. So I think maybe you could do a DP approach to this recursive part. My intuition says you probably could. After thinking through it for a few minutes, though, I think actually it'd be kind of complicated to actually pull that off because this target value makes things a little bit complicated. Yeah, I don't know. That's a good question. That's a good question. But overall, this is pretty quick. It's pretty quick, and we can spam our accepted solutions to raise our score because, I don't know. All combinations are needed even if the left side is bigger than the target because of the minus values. All combinations are needed even if the left side is bigger than the target because of the minus values. I'll do it by making all the possible combinations. All combinations are needed even if the left side is bigger than the target because of the minus values. Oh yeah, I agree. I see what you're saying. Yeah, I understand that. Yeah, you can't limit based off of that. Actually, what I was getting at was just being able to convert from a recursive solution to a dynamic programming solution. If there's a way to do that, dynamic programming means we're going to store like intermediaries. The previous results will store as sort of intermediaries in an array, which one, and I'm not sure if that really speeds things up, and two, I don't even know if we can do that. I think we can, but it's not obvious how to do that. We would want the you'd want to look at, I guess you would calculate these a and I minus 1, but you can't really have them stored because target minus v is not obvious at all what that would be. Yeah, you kind of, I don't know, man. I don't know. The way you would set up a dynamic programming version of this is not obvious to me. I think you can, but it's definitely not obvious, as I mentioned. But yeah, let me go. I'm gonna, yeah, because I spent a lot of time on this. I spent quite a bit of time just thinking about it too. Like this is a super interesting problem. I think what's really annoying about it though is that, like I said, it's really annoying that I TLE'd a bunch even after I spent like so much time working on it, because this part very clearly means like there's no way to do this without going through like an inordinate number of multiplicative terms. Yeah, unfortunately, there's just so many ways. Yeah, I don't know. I think this necessarily makes the problem combinatorial. In terms of asymptotic time complexity, I think this is necessarily combinatorial, so super exponential because of this part, just all the different ways you can create the multiplicative terms. I don't think it's possible to do better than exponential time, which is kind of a bummer. Like the thing that's frustrating about it is that, like, well, so this is just like the most efficient way to write a brute force solution, then like every solution is some form of an exhaustive solution, which is like, yeah, why I'm like really irritated by this, because there's just a lot of ways to write these solutions. Well, anyway, I don't know. I'm grateful that we got it. I'm grateful it's done, but interesting problem. Kind of really makes you think a bunch. Really don't like that it's just an exhaustive search that is, requires a lot of thinking to make it fast enough for this particular question and data set, I guess, something like that. Like that's kind of lame, kind of annoying. Grateful I have to think a little bit more about it, but also really irritated that it really is just like a brute force solution that's took me hours upon hours to write. That's it. It's like, what was the value of this? What was the point? Just to suffer. Just to suffer. Like, this is something that, like, you would probably never see in an interview. If you see one, like, I think they probably should just not ask a question like this, because it's way too hard. As mentioned, it just takes hours to figure out a faster version of an exhaustive search. That's it, I guess. And this would take me well beyond 45 minutes to code anyway. Even if I knew what to code, it would still take me like, not beyond 45. It might take me an hour just to code this, even if I knew what the answer was. Just because it's so complicated, so many pieces to it. Yeah. So anyway, all right, I'm gonna go. I think I've complained enough about this. So thank you again for watching, Mr. MGTOW Wolf, and anybody else who happened to be watching. I'm gonna go. Have a good rest of your night. I'm gonna get some food. Have an interview tomorrow, so that's gonna be interesting. I'm like, man, this is way harder than most of real life problems to solve. Yeah, I think so. But that's the thing, is like, people just kind of grab these problems offline. And apparently Google for a while was asking like LeetCode hard questions, which is like, some people do that. Some people will ask you LeetCode hard, which I know there's a guy. Good night. Yeah, I'm gonna go to bed in a minute. There's a guy that I know who, I guess he's like, I would say he's a friend, sort of. He's more like a friend of a friend, and the other person who I'd say is a friend is like a friend, more friendly than I'm friends, because like we never really hung out, never talked or anything. But I think he watched my videos like years ago, my stream years ago. But anyway, I think he popped in one day and asked me about like, oh, like what do you think about like giving a LeetCode hard to somebody in an interview, because he's like an engineer at a software developer at a startup, and I was like, oh yeah, sure, like LeetCode hards are, I mean they're hard, but not that hard, you know, some of them, but actually there's quite a range of variability when it comes to how hard the LeetCode hard problems can be. So like this one would be just so brutal to get, like you just wouldn't, nobody would get hired if they got this one. But other LeetCode hards you could do in like 10-15 minutes. So I don't know. I'm like responsible. I feel partly responsible for recommending like a LeetCode hard to somebody to use as a testing tool, which I don't think is actually fair. For like a question like this, I would say definitely not. But some other LeetCode hards are like you can do it, but they're definitely like brutal. So I don't know. Anyway, all right. Yeah. Good night. Talk to you soon. And yeah, I have mixed feelings about LeetCode hards, man. Largely should be avoided. I think it just generally should be avoided. Yeah, once I solve all the problems on LeetCode, I'm done. I think with LeetCode hards probably for my life. Just take a break. Take a break. But yeah, all right. Have a good night. Talk to you soon. Take care. And thank you again for watching.